Hello students, welcome to my YouTube channel Dear Mathematics and also welcome to the chapter of relation and function. In this particular session, we are going to discuss about the domain of a relation, range of a relation, then codomain of a relation and some of the problems based upon these fundamentals. So let us start from the domain of a relation. So here it is the definition of domain of a relation. Let R be a relation from the set A to the set V. Then the set of all first components or coordinates of the order pairs belonging to the relation R is called the domain of R. Shortly, it is denoted by dome of R. It is defined by the definition is in the set form like this. Dome of R can be defined as A such that the order pair AB belongs to the relation R. That means from the order pair just we have to choose the first component. Let us take an example. Let A set is equal to 1, 2, 3 and V set is equal to 4, 5. Then and let R be a relation from A to B defined by R is equal to, suppose it is taken as 1, 4 and 2, 5. Let us construct the arrow diagram. The arrow diagrammatic representation is like this. Just we have to make a graph of 1, 4, then 2, 5. Okay. Now we have to find out the domain of R. That means first of all we have to find out the first components of the given order pairs. The first component is 1, the second component is the first component of the first order pair, it is 1, the first component of the second order pair is 2. So here domain of R is given by dome R and it can be or it will be the set of two elements 1 and 2 because 3 is not attached with any element of the set V. So just we have to find out the first component or the first coordinate from the given order pairs. Then let us move towards to the another example. Suppose the B set is like this 6, 7 and 8. Let R be a relation from A to B given by R is equal to 1, 6, 2, 7, 3, 8. Then we have to find out the domain of R. The domain of R, the arrow diagrammatic representation is not necessary to find out the domain of R in the given problem. The domain of R is given by dome R and it is the set of all first components of all the order pairs. The first component of the first order pair it is 1. The first component of the second order pair it is 2. The first component of the third order pair it is 3. But here you can see that the domain of R is very much equal to the S set. In the previous problem or in the previous example, it was the subset of A set. But here the domain of R is equal to S set. That means it may be a subset of the first set or it may be equal to the first set. So domain of R may be subset of A or domain of R equal to A. So these are the two conclusions we can draw from the domain of the relation. Then moving towards to the range of a relation. Now discussing about the range of a relation. Again, let R be a relation from a set A to a set B. then the set of all second components or second coordinates of the given order pairs belonging to the relation R is called the range of R. It is shortly denoted by range of R, or it is defined in the set form like this: range of R is equal to collection of all second elements, that means the element V, where the order pair must belongs to the relation R. Let us take an example. Let R be a, okay, first of all let us consider two sets. Let A is equal to 1, 2 and V is equal to 3, 4, 5. Let R be a relation from the set A to the set V defined by R is equal to 1, 3, 2, 4. Then we have to find out the range of the relation. That means we have to find out the second components from the ordered pairs, not from the sets, from the ordered pairs. Range of R is defined as, or is given by set of all second components. The second component of this order pair, it is 3. The second component of the second order pair, it is 4. And you can see that this range of the relation R is the subset of V. That means here we have found range R is subset of V. Then let us move towards further another example. Suppose I have considered here, it is example number 4. The previous was 3, it is 4. Suppose I am considering here 1, 2, 3 and V set is equal to 4, 5, 6. Suppose the relation is given by, it is 1, 4, 2, 5, then it is 3, 6. Then we have to find out the range of the relation R is given by range R, and we have to find out all possible second components from all the order pairs. The second component is 4, the second component is 5, the second component is 6 here. And from this range of the relation, you can guess that, or you can say that the range of the relation R is very much equal to the B set. That means from the example number 4, here we have found that range of the relation R is equal to B. That means from the fundamental of the range of the relation, we get to know that the range of the relation, either it is subset of the second set or it is very much equal to the second set. Either of the case will happen in the range of the relation. So whenever the question will arise, domain of the relation is subset of, then you have to write down the first set. Either it is subset or it is equal to. Similarly, in case of the range of the relation, if the question arises like this, range of R is subset of, you have to write down second set. If the sets are given in the form of A and V, then you have to write down here A, and in the second step you have to write down here V. But basically we can say that the domain of the relation is a subset of the first set. The range of the relation is subset of the second set. Either case will happen. Either it is proper subset or it is equal to. Here also either it is proper subset or it is equal to. So this is all about the domain and range of the relation. Then moving towards to the codomain of the relation. Moving towards to the codomain of a relation, the definition is like this: let R be a relation from a given set A to a given set V, The set V, that means the second set. The second set is called the codomain of R. It is very simple on basis of the previous two. Example, let the set A is equal to 1, 2, 3 and the set B is equal to suppose 4, 5 and R be a relation from the set A to the set V defined by R is equal to suppose 1, 4, 2, 5, 3, 5, suppose like this. Don't go for the relation part, the given relation. We don't have to go for the given relation. Just look after the second set. Relation R is a relation from the set A to the set B. That means this is the second set. And this B set is the codomain. Codomain of R is equal to B. The second set, simply. We don't need to go for the relation. What is the relation? What are the first components? What are the second components? What type of relation is like this? Just we have to go for the second set. And the second set is B here because the R is a relation from the set A to the set B. That means the A set is the first set, B set is the second set. And just simply you have to put B set as the codomain of R. So it is very much easy on basis of the previous two, domain of the relation and range of the relation. So this is all about the domain of relation, range of the relation, and here it is codomain of relation. Now we are moving forward to discuss about inverse of a relation. Here it is the inverse of a relation. Moving towards to the definition of the inverse of relation, let A and B be two sets and R be a relation from the set A to B. Then inverse of the relation R is denoted by R to the power minus 1 and it is a relation from the reverse direction. That means from B to A. R is a relation from A to B. R is a relation from A to B. But R inverse is a relation from B to A. And what is the proper definition of the relation, inverse relation? It is like R inverse is equal to collection of all possible order pairs V and A. For all order pairs AB belongs to the relation R. That means we have to find out the reverse of all order pairs. That means we have to put the second component in place of first component and then we have to put the first component in place of the second component and we have to repeat this step for all possible order pairs that are present in the relation set. And then we have to construct a set by using those new order pairs and that set is called as the inverse relation. So it is all about the inverse of relation. Let us take an example so that it will be easy to understand for you. Here it is the example. Let A is equal to 1, 2, 3 and V is equal to, suppose I have taken here it is, okay, let us take it as 1, 2, 3 and V set is suppose like C and D. And R is a relation from A to B defined by R is equal to, suppose it is 1C, 2D and 3C. Here it is the relation. Then we have to find out the inverse of the relation. Inverse of the relation R is given by R inverse is equal to, just we have to change the positions of first component with the second component and we have to repeat the step for all order pairs present in the relation set. So it will be C1, it will be D2 and here it will be C3 and this is the R inverse, that means inverse of the given relation R. So it is all about the inverse of a relation. Then moving towards to the next step, just considering or just discussing about the binary relation. So here it is the binary relation on a set. These fundamentals are also to be discussed in the second year mathematics of your next year mathematics. So just let us give some brief discussion or brief analysis on the binary relation on a set A. Let A be any non-empty set. Then every subset of A cross A is called as a relation on the set A, because we have already discussed about the definition, very fundamental definition of the relation for the chapter Cartesian product and also relation and function. So we know that every subset of a Cartesian product is a relation. Every subset of a Cartesian product is a relation. Similarly, every subset of A cross A, because we are considering only one set. So here Cartesian product is A cross A. So every subset of A cross A is called the relation on A. Since empty set, that means phi is a subset of A cross A, so it is also a relation, and it is called as the empty relation, or also you can write down it as void relation. You can also write down void relation. Then in the note number 2, since every set is a subset of itself, similarly A cross A is also subset of itself. That means it is a relation on the set A, and here this relation is called as the universal set, because we cannot find out any bigger relation than the A cross A, that means than the Cartesian product of A with A. Then moving towards to the identity relation, we have to find out all possible order pairs in the form of A and A. That means the first component must be A and the second component must be A. In such similar pattern of order pairs are called as the identity relation. And here the identity relation is denoted by IA, and we will discuss about the empty relation, empty relation, universal relation and identity relation next year also in second year mathematics, 12th class mathematics. Just let us write down these notes, this will help in this year mathematics. Then moving towards some of the problems based upon today's fundamental classes. So let us discuss about some of the problems. So here it is the first problem based upon the domain, range, codomain and inverse of the relation. So let us go through the solution. What is the problem here? It has been given that let A is equal to 1, 2, 3 and B is equal to the set of 2, 4, 6. If R be a relation from the set A to B, that means A is the first set, B is the second set. Defined by the relation. The relation is already given here. 1, 2, 1, 4, 3, 2, 3, 4. That means just we have to find out the domain, codomain, range and R inverse. That means inverse of the relation. Just considering this relation, because the relation is already given to you. So it is very much easy. So given that A set is equal to 1, 2, 3 and B set is equal to 2, 4, 6. R is a relation from A set to B defined by R is equal to 1, 2, 1, 4, 3, 2, 3, 4. Just we have to find out these 4 things here. So first of all, dome of R. That means we have to find out all first components of all order pairs present in the relation R. And first components of all the order pairs are 1, then it is 3. 1 and 3. Then second, we have to find out codomain of R. Codomain of R is very much easy. We don't need to go for the relation, just I have to find out the second set. So codomain of R is the second set. R is a relation from the A set to the B set. That means this is the second set and the second set is the codomain. We don't need to go for the relation. Then third, the range of R. The range of R is defined by identifying the second components or coordinates from the relation 2, 4, 2, 4. That means it is 2, 4. The fourth, we have to find out the inverse of the relation. R inverse, just interchanging the first component or second component of all the order pairs that are present in the relation R. We have to just change their position. That means it will be 2, 1, it will be 4, 1, it will be 2, 3 and this is 4, 3. And here it is the result for inverse of the relation. And here it is the solution of the first problem. Then moving towards to the second problem. Here it is the second problem, and the problem is like this: A set and B set are given to you. The A set is 1, 2, 3, 4, 5, and B set is 1, 4, 5. R be a relation from the A set to B set. That means from this step you have to clear that A is the first set, B is the second set, and it is defined by order pair of AB such that small a belongs to capital A, small b belongs to capital B, and the relation is defined as A is less than B. Then we have to find out these things from the given relation, this given condition. First of all, we have to find out the relation, and it is in the I bit. Then after finding out the relation, you can find the next 4 things easily. So let us go through the solution. Given that A is equal to 1, 2, 3, 4, 5 and V set is equal to 1, 4, 5. R is a relation from A to B defined by R is equal to order pair of AB such that small a belongs to capital A, small b belongs to capital B, and A less than B. That means R set can be defined as, the relation is like that: first component must be less than the second component. 1, 4, 1, 5, 1, 4, 1, 5. We cannot consider 1, 1 because they are equal with each other. So 1, 4, 1, 5, then 2, 4, 2, 5, then 3, 4, 3, 5, then 4, 5. You cannot consider 4, 4 because 4 is equal to 4. You cannot consider 4, 1 because it is greater than. Just we have to consider such type of order pairs in which the first component must be less than the second component. So these are the all possible order pairs that can be placed in the relation R. Then moving towards to the second bit, we have to find out the domain of R. That means we have to find out all first components from these order pairs. So it is 1, 2, 3, 4. You can see that 5 is not present in the domain of R because 5 is not in the first component. 5 is not present in the first component. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, it is done. Then moving to the third point, we have to find out the range of R. That means we have to find out the second components from the relation R. 4, 5, 4, 5, 4, 5. That means it is 4, 5. Then moving towards to the fourth bit, we have to find out the inverse of the relation. That means R inverse, and it can be defined by just interchanging the first component with the second component from the relation R in all order pairs. That means it will be 4, 1, 5, 1, 4, 2, 5, 2, 4, 3, 5, 3, then 5, 4. It is the R inverse. Then moving towards to the codomain of R. Codomain of R, again I am repeating, it is none other than the second set. R is a relation, you can say that R is a relation from A to B. It is first set, it is second set, and here it is the codomain. Second set is the codomain, that means B is the codomain for the relation R. So it is all about the second problem. Then moving towards to the last problem of this current video session. Here it is the most important problem of this current video session and as well as the last problem. Given that the A set is like this 2, 3, 4 and B set is the set of the elements 6, 7, 8. R is a relation from the set A to the set B defined by R is equal to collection of all possible order pairs A and B such that the small a belongs to capital A, small b belongs to capital B, but the condition is like this: A divides B. That means the first element must divide the second element. Then we have to find out in 2 phases. First of all, we have to find out R, the relation R from the given condition. Then we have to find out R inverse from the R. Then in the second phase, the important case is here. Just we have to show that the domain of the relation R is equal to range of R inverse. Then in the fourth case, we have to prove that the domain of R inverse is equal to range of R. That means range of the relation. So let us go through the given data first. Given that A set is equal to set of elements 2, 3, 4 and B set is equal to the set of elements 7, 8. Let R be a relation. Okay, given that R is a relation. It is given that and R is a relation from A set to B set given by R is equal to order pair of AB such that small a belongs to capital A and small b belongs to capital B, and the given relation is here or condition is here A divides B. That means the first element divides the second element. Then we have to find out relation R from the given condition. R is equal to 2, 6, 2, 8, then 3, 6, then 4, 8. You can see that all of the first elements are dividing the second elements. That means the second element is divisible by the first element and the first bit is clear for you. Then we have to find out the second bit. That means we have to just interchange the first component and the second component in all of the order pairs given in the relation R. So R inverse is defined as it is 6, 2, 8, 2, 6, 3, 8, 4. So here it is the second bit. That means the solution of the second bit is here. Then we have to find out, before going to the phase of the third bit and fourth bit, first of all we have to find out all of the cases, domain R, range R, domain R inverse, range R inverse. Okay. So first of all let us find out domain R. Domain R. That means we have to find out all of the first components from the relation R. 2, 2, 3, 4. That means 2, 3, 4. Then we have to find out range R. That means we have to find out the second components from the relation R. The second components are 6, 8, 6, 8. That means just we have to write down a single time because any element cannot be written twice or thrice more than one in a set form. Then we have to find out domain R inverse. Domain R inverse. That means we have to find out the first components from the R inverse. We have to find out domain means first component. First component from the R inverse. And this is 6, 8, 6, 8. That means it is 6, 8. Set of elements is 6, 8. Then range of R inverse. Range of R inverse means, range means finding out the second components. Finding out the second components, but from the R inverse. So R inverse second component 2, 2, 3, 4. That means it is 2, 3, 4. Okay. Now we have to go through the third bit and fourth bit of the given question. Just let us compare. You can see that domain of R is equal to range of R inverse because both of the two sets are giving the results in the set form 2, 3, 4 and they are equal with each other. So here we have domain of R is equal to range of R inverse, that is equal to 2, 3, 4. That means third bit is proved here. Third bit is proved. You can write down also third bit here. Then in the fourth bit, again we have from the above. You can also write down from the above. From the above. Again we have, you can see that range of R 6, 8, domain of R inverse. That means domain of R inverse is equal to range of R, and both of those two sets are in the form of set of the elements 6 and 8. That means IV is proved here. That means the problem has been solved here. The first bit, second bit, third bit and fourth bit. This problem is very much important because of these two cases. You have to remind or you have to remember these two cases. That means domain of R inverse is equal to range of, domain of R is equal to range of R inverse, and also domain of R inverse is equal to range of R. So it is all about the third problem or solution of the third problem. You can say that So today in this video we have just discussed about domain of a relation, range of a relation, codomain of a relation, then inverse of a relation, and also binary of a binary relation on the set A, on a single set A. So just we have completed all of the fundamentals of the topic relation. In the next topic we are going to solve some of the problems of your book. Till then, thank you.